last time I said that we don't really have a product rule, quotient rule, or chain rule for antiderivatives. But today we're going to learn a technique that's going to help us deal with chain rule type problems. And this is the technique of substitution. We're going to use this to find antiderivatives or indefinite integrals. So before we get started, I need to define something called the differential. And the differential dy is defined to be the derivative f prime times dx, which is really another differential. This is really just a calculus way of saying that your change in y equals your slope of the tangent line times your change in x. But what we need to know for this class is just how to compute the differential. And to compute the differential, it really isn't any different than finding the derivative. So the derivative of 5x squared plus 3x is 10x plus 3, and then you just multiply by or put a little dx at the end. That's the only thing new here. So to find the differential of y equals e to the 4x, this would be a chain rule problem. The derivative of e to a power is e to a power. And then the chain rule says I have to multiply by the derivative of what's inside the exponent. So in this case, I have to multiply by 4. And then I put the little dx there. Okay, so we are going to be using differentials when we do this technique called substitution. And so I have written out the steps that we're going to take. But I think what I'm going to do is just show you an example of how this process works. So to use this technique of substitution, we're basically doing a change of variables. And so we are going to pick something in that integrand to be our u. And usually, if there's something inside another function, if there's something in parentheses or in a square root, that's a good choice for your u, kind of like when you're doing the chain rule. In this case, I'm going to pick the 5x squared minus 2 to be my u. So that's step 1. And then step 2, I'm going to compute that differential du, which in this case would be 10x dx. Now my goal is to change this integral in terms of u, to take the integral, rewrite it in terms of u. So what I'm going to do is I'm actually going to take my differential and I'm going to solve it for dx. To solve this for dx, I would just divide by 10x. So now my integral, I have this 10x. The 5x squared minus 2, that's my u. So then I have a u to the third. And then I replace the dx with the du divided by 10x. And the goal is to get the integral to have u's in it only, to have no x's left in the problem. And I can tell that the substitution I've chosen is going to work because these 10x's will cancel out, and I am just left with u to the third du. So again, the goal is you cannot have any x's in your problem. And so you choose a u such that its derivative, the du, is also within the same problem. That's kind of the concept here. Now this is something that we can integrate. Let's see, we would get u to the fourth over 4, and then of course plus c. And then to finish the problem, we have to rewrite this in terms of x. And so I'm going to replace that u with the 5x squared over 2. And that is my final answer, my antiderivative. All right, let's do a couple more examples. In part B, I think I'm going to choose the x squared to be my u because the du is going to have an x in it. So I'm choosing the x squared to be my u because I see an x within the problem as well. Now, with these problems, if you don't choose the correct thing to be your u, what's going to happen is your x's aren't going to disappear, and then you just know you have to choose something else. So if u is x squared, my du is 2x dx. Solve for dx, that means dx would be du divided by 2x. I'm going to rewrite the integral, so I've got that x, e to the u, and then the dx becomes the du divided by 2x. I can tell the substitution is going to work because the x's cancel out, and I'm left with something that has u's only. To integrate this, I'm going to take that divide by 2, which is a 1/2. I'm going to pull that out front, and then I'm just left with an e to the u du. And so when I integrate, I get 1/2 e to the u plus c. And then finally, I rewrite this in terms of x. Let's see, our u is x squared. So 1/2 e to the x squared plus c. Example C. For this one, I think I'm going to try the denominator as my u. So u is x squared plus 2x plus 4. Then my du would be 2x plus 2 dx. If I solve for dx, I get du divided by 2x plus 2. I'm going to rewrite my integral. So that denominator was my u, and the dx is a du divided by 2x plus 2. Let's see, can I get the x's to cancel out? Yes, I can. If I notice that I have a greatest common factor of 2 in that denominator, and so now I can cancel the x plus 1's. I'm going to take that constant of divide by 2, pull it out front, and I'm left with a 1/u du. So let's see, to integrate, I get a 1/2 natural log of the absolute value of u, of course, plus c. And then finally, I'm going to rewrite this in terms of x again, and that's my final answer. All right, example D. This time, I think I'm going to make the u 3x minus 4. So then my du would be 3 dx, and dx is du divided by 3. So my integral is 5 divided by u, du divided by 3. I'm going to pull those constants out front, so now I've got 5/3, 1/u du. I integrate, I get 5/3 natural log of absolute value of u, of course, plus c. And then finally, I am going to rewrite this answer so it has x's. I replace the u with the 3x minus 4. And that's my final answer. Now, I do want to take the time to make a little bit of a side note here. One common mistake that I'm noticing is that when people see 1 over something, it's natural to say, oh, this is going to be a natural log. But it's only 1 over x or 1 over u that gives you a natural log. If you have something else, like 1 over u squared, we would have to rewrite this as u to the negative 2, and then we could use our power rule to integrate. Negative 2 plus 1 is negative 1, divide by negative 1, and that would give me negative 1 over u plus c. So again, you only get that natural log when you have a 1 over x to the 1. If there's other exponents, it doesn't give you a natural log. All right, one more example. Let's see, I'm going to pick a u. I think I'm going to pick the thing inside the square root, the x plus 3. So then my du would be 1 dx. There isn't really any solving to do here. Dx is the same thing as du. And so if I rewrite this integral, let's see, I would get x square root of u du. And so I have a little bit of a problem here in that the x didn't disappear. To integrate, we can only have one variable. We can't have x's and u's. And so at first glance, it looks like the substitution didn't work. But in this case, there's a little trick we can do. We can take our expression for u, and we can actually solve it for x by subtracting the 3. So x would equal u minus 3. And then I'm going to take that expression and plug that into my integral. So x is u minus 3. And then I think I'm going to change that square root to a 1/2 power. Now my integral has one variable only, has u's only. There's no product rule for antiderivatives, but now that I've done the substitution, I can actually distribute the u to the 1/2 and get rid of that product. To distribute, we add the exponents, so u to the 1 times u to the 1/2 would be u to the 3/2. And then I have a minus 3 u to the 1/2. And now this is something we can integrate. Let's see, 3/2 plus 1 is 5/2, so I get u to the 5/2 divided by 5/2 minus 3. And then 1/2 plus 1 is 3/2. So u to the 3/2 divided by 3/2 plus c. Dividing by fractions is the same thing as multiplying by their reciprocals. And 3 times 2/3 is just 2. And then finally, I am going to write this in terms of x, and then I'll be done with the problem. So let's see, we said u is x plus 3. And this kind of complicated expression is my final answer. So in some cases, if you do the u substitution and you can't get rid of all the x's, you can take your expression for u and just solve it for x and plug that in. That's it for today. Let me know if you have any questions.